Alright, so this is the last lesson for chapter 4. We're going to be looking at simple harmonic motion. Now before we go over to all this period stuff, let's actually look at what simple harmonic is and describe the energies throughout. Okay, so simple harmonic motion really just is anything that repeats itself over and over and over again. Right, so usually in class we do an experiment with a spring where you have a spring and then you throw a weight on there and drop it. And what happens to the weight? Well, it just goes down, comes back up, down, up, down, up. And that just repeats over and over and over and over again. Now the cool thing is the period will always stay the same. Now there is internal frictional forces and external frictional forces if you want to even include air resistance. But so there's never a perfect scenario. There's no such thing as a machine that doesn't lose energy. So it will lose energy, and the energy is related to its amplitude. So its amplitude will just slowly die off over time, but it will still keep perfect time. The period doesn't change. Okay, and that's actually kind of cool, because if you think about it, if it has a large amplitude, well, the more stretch you actually have on the spring, the greater the retarding force on it, and therefore the greater the acceleration. Right? And so that makes it just much faster over a larger distance. But if you have a much smaller amplitude over a smaller distance, you have a less retarding force because the spring is stretched or compressed less. So it's actually moving slower over a smaller distance. Fast over a large distance or slow over a small distance. So it does keep really good time. However, we're going to look at simple harmonic motion. Simple harmonic motion we say is simple because we're going to ignore all of those frictional forces and the fact that it's just going to be perfect, keeping the same amplitude. Right? Now in real life we don't actually want that. In real life we actually want the amplitude to drop off. We call it damped harmonic motion. Okay, so imagine you're in your car and you have suspensions so that when you go over a bump, right, your car sort of bumps, but you want that bumping to stop. Imagine you had some sort of magical simple harmonic oscillators over your car. You go over a bump, your car's just going to go like up and down forever, never losing any energy, never stopping. That makes me feel sick. Okay, so we don't want that. But for the case of analyzing the system mathematically, it's a lot easier to analyze it with simple harmonic motion. So that's what we're going to analyze today. Okay, now on the back, we're going to start with the back actually. We have two examples of simple harmonic oscillators. We have one that's is going back and forth, and one that's going up and down. So we're going to analyze these. Let's start with the horizontal simple harmonic motion. So let's say we have a wall, and we attach a spring, and we take that spring and we stretch it beyond its equilibrium position right here, x equals 0. And it's got some mass on the end of it. Okay, and when we let go, what's going to happen is it's going to fall inwards, right? Eventually to, how many of these diagrams I'm just going to do towards the equilibrium position. Momentum will keep it moving more inwards. Well, I shouldn't say momentum, inertia, because technically we haven't learned momentum yet till chapter 5. So inertia keeps it going, and it gets compressed to some maximum amount. And then on your diagram, it keeps going back and forth, back and forth, back and forth. So I'm just going to draw half a cycle. Okay? The other half you can infer. All right. So when it's fully extended, what kind of energies do we have present there? Well, if it's stretched, we have elastic energy. And that's, since it's fully extended, our elastic energy is at a maximum. Okay, same over here. When it's fully compressed, our elastic energy is at a maximum. Okay, what about here? Well, if that's our equilibrium position, it's not stretched or compressed. So the elastic energy is actually 0. So what energies do we have there? We have to have something, right? This energy doesn't just disappear in the middle. It gets converted, but to what? If you said kinetic energy, you're right. Right? So at this point, kinetic energy will be a maximum. So we're oscillating between converting elastic to kinetic, elastic to kinetic, elastic to kinetic, going back and forth, back and forth. Okay? Now, in between these phases, right here you have a force, right, which is in this direction. And this is interesting later when we analyze the period. If you want to make, let's say, our x value positive in this direction. So right now, let's look at a position somewhere in between these positions. So there's a force acting on that. It's in a positive x direction, but the force is in the opposite direction. This is why a lot of the times Hooke's law is written in textbooks as F equals minus kx, right? Because the force acting on the object is always in the opposite direction that it's pulled or compressed in, right? If it's compressed, like somewhere here, right? Well, it's being compressed in this direction, but the force is going to be in that direction, right? So we have a retarding force there. And because of that, right here, as it's coming back, it's going to be accelerating. Right? It's actually, in this case, going to be getting faster as it moves this way, increasing speed, and then over here it's going to be accelerating, getting slower, right, in the other direction until it stops, then go faster, and so on, if you want to think of it in terms of forces. Okay, so that's our horizontal example. Notice we never had gravitational potential energy in that case because it's not being lifted up in a gravitational field. Not so in our vertical example. So let's say we have a vertical example. This time, we're just going to start at our equilibrium position. So it's just hanging there in equilibrium, and then we attach some mass to it. When you attach a mass to it, it's going to fall, and it's going to continue to fall. Again, I'm just going to look at half the cycle. You can infer the other half. All right, so at this position, let's say this is our maximum x value. So I'll write x equals max. Let's say this is half the max value, so x equals half our max value. At this position, what kind of energies do you have? Definitely have gravitational. Let's assume this is where we're going to say h equals 0. Okay, we'll write that down here, h equals 0. So up here we definitely have gravitational. Gravitational is at a maximum. Do we have kinetic? No. No. Even if it's bouncing up and down, that top part is where it changes direction. So that's where its velocity goes to 0. So no kinetic energy. So kinetic energy is 0. How about elastic? No, that's its equilibrium position. So no elastic. Elastic is also at 0. Okay, what about at the bottom? Stretched as much as it's going to stretch. That's the point where it changes direction and starts coming back. So now elastic energy is at a maximum. If it changes direction there, kinetic energy is 0. And if it's at a height of 0, well then gravitational potential energy is also going to be 0. All right, those are our two extremes. What about this middle point? Well, this is the fastest point it's going to get. Right here it accelerates, it gets faster and faster, and then what happens here? What happens at this point is the force of gravity acting down on it is going to be equal and opposite to the spring force acting up on it. So at that point, your net force is 0, you don't accelerate. But your inertia keeps you going. If you're going down, your inertia keeps you going down. If you're on your way up, your inertia keeps you going up. But let's assume we're going down at this point. If we're on our way down, suddenly this is going to become greater than gravity if we fall below this point on our way down. At that point, your acceleration is going to be up. So you're going to, since your direction of velocity is down, your acceleration up. In this section, you're going to slow down. But in this section, you're going to speed up, because in this section, gravity is stronger up here. Right? And so you'll actually speed up. So at that magical point where we have velocity at a maximum, our kinetic energy is a maximum. Okay? Looks like gravitational potential, if that's half your height, which it would be, right, is at half. Right? And elastic potential energy, well, elastic elastic potential energy is proportional to x squared, right? So I wouldn't actually say your elastic potential energy is half there, okay? The value is half, but since it's squared, your potential energy would not be half. Okay? Okay, so now that we know this, let's try a couple questions. We're going to try the first 2 questions, and then we're going to talk about the period of a simple harmonic oscillator before we go on to question 3. So the first question says, below is an example of a mass spring system undergoing simple harmonic motion at maximum compression in figure A, which is here, and it's just saying that this is 12 centimeters. And maximum extension at figure B, which is an extension of 38 centimeters. Terrible 8. Okay, at what length of the spring is the speed of the mass at a minimum? So this is where you need to go back and look over what we talked about for the horizontal simple harmonic oscillator. So where's the speed at the minimum? Well, either at maximum extension or maximum compression, because that's where it changes direction. Okay, so the speed is 0 at here or here. There you go, part A done. B says at what length of the spring is the acceleration of the mass at a minimum? Okay, where would your acceleration be at a minimum? The only forces acting on this is the spring force, and your spring force will be at a minimum, well, 0, right? And therefore your acceleration will be 0 at your equilibrium position. But where that would be x equals 0, right? But if we're measuring from this wall or edge, where would that be? Well, it's right in between these. So you can take 38 plus 12, which is 50, divide by 2. Okay, so it'll happen at 25 centimeters from the wall. And it says, what's the amplitude? Well, if this is at our equilibrium position, is at 25 centimeters, the amplitude is either this distance or this distance, which is the same. If you remember doing waves, okay, there's your equilibrium position, that's your amplitude, and that's your amplitude. They're the exact same. It's the same with this oscillator. Okay, and you can prove that, right? 38 minus 25 would be 13, or 25 minus 12 would be 13, right? So your amplitude is 13 centimeters. Okay, so that's it for question 1. Let's move ahead and try question 2. Question 2 says the maximum energy of a mass spring system undergoing simple harmonic motion horizontally is 5.64 joules. So maximum energy, that means total energy, is 5.64 joules. Here's the question. The mass is 0.128 kilograms. And a force constant or a spring constant, K, is 244 newtons per meter. Question A, what is the amplitude of the vibration? Okay, we still need to remember all the energies in that simple harmonic motion and conservation of energy. Now it wants to know what the amplitude is. So at the amplitude, whether or not that's maximum extension or maximum compression, what energies are present? At that point, you're not moving right here or here. You don't move for an instant. So you don't have any kinetic. All your energy is elastic potential. So we can say that this total energy is equal to elastic potential energy at our amplitude. Or I can say at x equals A. And so we know total energy is 5.64. Okay, our equation is 1/2 kx squared, but this is at x equals A, so ka squared. you just rearrange this all for A. So A is the square root of 2 times our total energy over K. If you plug in your values, you get 0.215 meters. You go, or 21.5 centimeters. Okay, part B is very similar, but it says what's the maximum speed? Maximum speed happens in the middle, right? At our equilibrium position, where all of our energy, all of it, is now kinetic. So it's very similar to this question, except all of our energy is now kinetic at x equals 0. So we can write our total energy as equaling to 1/2 mv squared. And now we're just going to solve for v, which is the square root of 2et over m. Right? Plug that into your calculator, and you get 9.39 meters per second. Right? So that's part B. Part C is a mix. Find the speed of the mass when it's 15.5 centimeters from the equilibrium position. So that's not at equilibrium, and that's not at amplitude. Somewhere in between. So what energies are present? Well, both elastic and kinetic. So at that point, our total energy is going to equal to kinetic and elastic. Okay? It's not hard, just a little bit more mathematically tedious here to solve the equation. So you have ET equals to 1/2 mv squared plus 1/2 kx squared. You know everything there except for v, and that's what you're solving for. Okay, so if we're solving for v, v equals the square root of 2et minus kx squared all over m. Okay, so plug that into your calculator, you get 6.51 meters per second. Okay, everyone all right with that? There's nobody here to yell at me for going from here to here in one step, if I like that. Okay, try it yourself though. It works. Alright, now before we move on to question 3, let's go back and talk about the period of a simple harmonic oscillator. And we're going to compare it to circular motion. Why are we going to compare it to circular motion? Well, let's say we have my tennis ball. Oh, it's my tennis ball. Okay. Racer. Okay, now a racer undergoing circular motion. This is a repetitive task, so we can say it has a period. Okay? But if I take this and move it perpendicular, I can get it perfect with the camera. Right? Other than the fact it looks like the racer is magically getting smaller and bigger because it's getting closer and further away from the camera. It looks like it's just doing this. Just moving up and down. Okay, which is our simple harmonic oscillator. So we can compare the two. It actually works perfectly. So if we had a spring, I'm just copying the diagram on your front page here, just not as well. And here's our equilibrium position. That's terrible. Okay. Here is an object undergoing circular motion. If this is x equals 0, well, this distance is our amplitude. This distance is our radius. Our amplitude and our radius is the same thing. Now with circular motion, we calculated centripetal acceleration. We usually used v squared over r, but I derived 2 other formulas for you. And since we're interested in period, the time it takes for one cycle, let's remember that that equation is 4 pi squared r over period squared. Okay, well, I'm just going to rearrange that for period. So period equals 2 pi times the square root of r over ac. Okay, let's move on from that. Now, if we look at this diagram, one, we know that r and a are the same. So I can rewrite that as period equals to 2 pi times the square root of A over AC. All right, now let's look at forces. Now, I said that if we're extending, right, if x is in this direction, that stretch, there's a retarding force wanting to pull it back. So the force is in this direction. So if we're to apply Newton's law and say, like, sum of all forces equals ma, and pick a point like this direction, okay, well, all of our forces is, what force do we have? Hooke's law. So we have our F squiggly force. F squiggly equals mass times acceleration. Okay. And we know from Hooke's law that this is kx. Okay. So this is, I'm taking obviously this direction to be our positive direction. That's why I have ma is positive and this is positive. Okay. Always choose acceleration to be the positive direction. Just makes things easier so you don't have to deal with negatives. Equals ma. And then I'm going to rearrange this equation a little bit. So I'm going to write it as, is it m over k? So let's bring the k down here. And let's bring the a over here. Equals x over a. Now if you look at this, here we have, this is ax because it's linear. But ax is the same as ac. The accelerations are the same. At least the magnitudes are anyways. Okay? And x, well, x is our value for a. They're the same. Right there. So I can replace this with t equals, I'm running out of space here, t equals 2 pi times the square root of, I just erased it, m over k, m over k. Okay, and that is the period for a simple harmonic oscillator. Okay, now there is another way to derive that using calculus, which is really cool, but you need to know integration, and I know you don't do integration, but I'll show you the video. It's an old video, but it's a pretty good video, so I'll post that as well so you can look at it. So now we can go back and look at question 3. This one's easy. It's just plug and play now that we have the period. It says, what mass hung from a spring of force constant 140 newtons per meter will give a mass spring system a period of vibration of 0.85 seconds. Okay. So if we are solving for mass, well, if you look at that, how do you solve for mass? It's in a square root. So what should you do first? Let me write this up here. So if you said square both sides, you're right. Square both sides. So t squared equals 4 pi squared times m over k. Okay, now you can rearrange for mass. Mass equals t squared k over 4 pi squared. Then we plug in what we know from the question, which is the period is 0.85 squared. The spring constant is 140 over 4 pi squared. And we get our mass, 2.56 kilograms. Okay, so that's that. On Monday or all next week, we'll do chapter 5 on momentum. And then I'll feel better that I spent more time covering all this. Also make sure Tuesday, our meeting with IQC, the Institute of Quantum Computing, at 2:20 online. Okay, try not to forget about that. It's going to be really cool. Have a good weekend.